Hi, so hello everyone. Today we have Hao from IPMU in Tokyo. And he'll be telling us about this very interesting paper on strain perturbation theory and the appearance of symmetries. Please take it away.
Okay, thank you very much for a nice introduction. It's my great pleasure to be invited to give a talk here at TIFR. And today I'm going to talk about space-time manifestation of worldsheet non-invertible symmetries. So it's based on a paper I had with Justin Kaidi and Yuji Tachikawa back in February this year. By the way, I remember that the talk could go as like the maximum time is 2 hours and 15 minutes. Is that correct? But is there a is there a standard set of time? Like, is it more targeting to 1 hour and 1.5 or 1.5 hour? Maybe I should ask earlier.
You can target 1.5 hour.
1.5
So
hour.
the talk it does go long, but the speaker is not supposed to know it.
Sorry, I know too much. I heard too much. Okay, so this talk will have like starting from part 0, which is backgrounds and motivations, and then I'll be going into part 1, which is string scattering on non-Abelian orbifold space-time. So here I will be revisiting the old story known in the 80s, but try to package it in the new language of non-invertible fusion algebra. And in part 2, I'll try to generalize and study the fact of, given the fusion algebra on the string worldsheet, what can we say about the scattering amplitudes in the space-time at tree level versus loop level? And we try to make a statement and then prove it with some mathematical rigor. And this is the main part. And if time permitting, which also depends on how much questions I get during the talk, I will also mention a part 3, which is how some generalized global symmetries in strong constructed QFTs can be detected from the worldsheet perspective. So let's start from backgrounds. As you have probably all heard of, the program of generalized global symmetries is try to rethink of the global symmetries as associated to topological operators. So the generalization is 2 steps. So you first reformulate the ordinary global symmetries as codimension 1 topological operators so that they carry a group element, and the topological operator carry a group element, and the charged state carry more precisely an element in the Pontryagin dual group. So once the topological operator crosses the charged state, it assigns a phase to the charged state. So it's like exponential of this pairing between G and G naught. So this is how the abstract notion of group action is made more physical of having a topological operator crossing a charged state. And then one can realize that the topological operators doesn't have to be codimension 1, but it could have higher codimensions. So terminology-wise, a codimension n+1 topological operator is supposed to is thought of as an n-form symmetry, and when n greater than 0 is called a higher form symmetry. And we know they're abelian because, like, when the codimension is higher than 1, there's no canonical notion of ordering, and you can permute one topological operator around the other without any physical effect. So the group has to be abelian. And by linking, they charge, or at least canonically, they charge n-dimensional operators / excitations. So the charged object becomes extended as opposed to point-like. So for example, a one-form symmetry operator, which I draw in blue, will be codimension 2 in the space-time, and the charged object is one-dimensional. So they link. So again, they link in a total space-time, and they carry charge in an abelian group H1 and the Pontryagin dual of this abelian group. so that when you delink, so this delinking is a geometric / topological generalization of this crossing in the zero form symmetry case. For example, this 4D U1 Maxwell theory has a U1 times U1 one form symmetry, with one of the U1s being the electric symmetry charging the Wilson line, and the other magnetic one form symmetry charging the Tooth line. So the charge operators will be Gauss surface, etc. And
How?
let's
Is it that these line operators can only be charged under one form symmetry, or can they take charges from also lower form?
in more subtle examples of non-invertible symmetries, there could be a symmetry of particular form charging charged operators of not exactly like a p-form symmetry, not just charging p-dimensional operators, but also maybe higher dimensional operators. So this is just one simple example where these Wilson lines and Tooth lines are charged by are charged under the one form symmetry.
No, but I was just thinking of a cylinder wrapping the line instead of a circle, so that doesn't happen.
A cylinder wrapping, let's see. Let's see. So actually a cylinder is topologically more closer also to a circle. Like if you want 3D space-time just for intuitiveness, then like a codimension one topological operator is like a sphere. And for cylinders, yeah, so it behaves closer to a one form symmetry topological operator.
The difference would be that the cylinder would also be able to wrap point-like objects, right?
So yeah, as you correct, yeah, as you said, this cylinder can wrap an object that's on its axis, but the cylinder will have boundaries, so you need to decide what you want to do with the boundaries. Yeah, so that introduces extra complication.
Okay, thanks.
Sorry, why would we have boundaries? I mean, if the charged object of interest is a circular object, then the cylinder could just be like a torus wrapping that circular object. For example, you imagine a bunch of charges arranging themselves in a line, a wire with a bunch of charges. And in order to capture that charge, you do have to wrap it with a torus, right? So maybe you should think, maybe in that case, it is thought of as just a, smearing of point-like charges or something like that.
Yeah, interesting. This type of linking involving non-trivial topology of the symmetry operator hasn't been the main focus of the research, but it's certainly interesting to consider. Yeah, thank you for your remark.
Also, it could be non-Abelian, right? This order argument doesn't work anymore.
Sorry,
Okay.
could you? Okay, sure.
No, the order argument doesn't work anymore because it's a torus and not a line, so you can't take. It could be non-Abelian like this. If it is charged under this symmetry, then it could be non-Abelian.
If it's charged under this symmetry, it could be non-Abelian. I see.
Yeah, but I think that's a tangent. Thanks.
Yeah, it's also a question of how many form you call that thing. It might be good to introduce new terminology for that. Yeah, but thanks, it's very interesting. Okay, so then come to non-invertible symmetries. So algebraically, one doesn't need to require that symmetries obey group laws. So like with symmetries described by group laws, and element in a group always have an inverse, but you could formally wonder what happens if a symmetry operator does not have an inverse. So at least the mathematical structure to describe some fusion without inverse is I said fusion category, but what I only need is fusion algebra for today. So a fusion algebra C with a bunch of elements and some fusion rules that result in a formal sum of elements, potentially with coefficients in the same fusion algebra. And for example, one most commonly encountered fusion algebra is the Tambara-Yamagami fusion algebra with group Z2. so that there's identity and there's the order 2 invertible element eta, which squares to 1, and there's a non-invertible element script call n, so that call n squared is 1 plus eta, but also call n absorbs eta both from one side and from the other side, so that this n has no inverse. And the physical realization are well known to be duality defects, which are long known to be realized in 2D systems, either in lattice and in continuum. So for example, the 2D Ising model on a square lattice at critical temperature will have this n and be realized by the duality interface between the, like perturbatively, you can have a low temperature phase and a high temperature phase, but you can go to extrapolate a non-perturbative region and make them both reach the critical temperature, so that you get the duality interface within the same system that's described by n. And here, eta is the Z2 spin flip symmetry. And you can get that implementing n twice amounts to summing over all spins, so you get 1 plus eta. And similar stories can be told in the 2D continuum. So it's in Ising CFT, where you gauging Z2, you get a new system that's isomorphic to the original theory, and that also results in this duality interface n. And some development 3 years ago, so by going into higher dimensions, I think we need it's also nice to mention the early study of higher form symmetries in high dimensions as some preparation. So one noteworthy paper is this paper by Aharoni, Seiberg, and Tachikawa in 2017 called Reading Between the Lines of 4D n equals to 4 SCFTs. And here they basically said that for a 4D n equals to 4 super Young Mills, you need to not only specify a gauge algebra, but also to specify the line operator content, which algebraically corresponds to specifying a global form of the gauge group, and sometimes some discrete torsion data. So for example, this SUN, among all the super Young Mills labeled by the gauge algebra SUN, you can first have one that's labeled by the gauge group SUN, and it has a Zn electric one-form symmetry, which physically means that the collection of line operators are only genuine Wilson lines, and also the SUN mod Zn super Young Mills theory with trivial discrete theta angle, where the only genuine line operators are toothed lines. And in more general, you can have theories with non-trivial discrete theta angles. So then the the genuine one-form operators will be dionic lines. And both SUN and SUN mod Zn theories have identical gauge dynamics of the Lie algebra SUN, but as I said, they're different in the spectrum of extended operators. And they're related by SL2Z transformations. So the SL2Z transformations that can be expressed in terms of S transformations and T transformations will map among these global forms of gauge groups with particular discrete theta angles. So they exchange these different for the n equals to 4 super Young Mills theory of SU4, for example. And in the next slide, this relation will be used in constructing the non-invertible, in one construction of the non-invertible symmetry in 4D. So
what does the subscript mean in this this T and S transform SU4 mod Z subscript 1?
Thank you very much. So I should have clarified the notation. So for SU4 mod Z4, for example, there's a subscript that's also mod 4. And it basically means the discrete theta angle term of theta over 2 pi trace of wedge f wedge f, the topological term that you are putting in the system, and it will affect whether it is the magnetic line or it is the dionic line that is the genuine operator in this theory. And similarly for this SU4 mod Z2, basically plus should be taken to mean 0 and minus should mean 1. Yeah, thank you for this question. And I was basically taking a screenshot from this paper, and the notations are explained there if you're interested in more details. So also what will be used in these constructions is what's the meaning of gauging a discrete symmetry, possibly a discrete higher form symmetry. So the formulation is quite different from gauging a continuous symmetry in that we are not coupling the background field to some current, but when gauging a discrete n-form symmetry labeled by G superscript n, we are summing over all G values of the n+1 form background field B. In other words, we're summing over all topological sectors of configurations of this discrete symmetry. So in terms of the partition function, let's say the original partition function is Z, and we can have it depend on the background field B of this gauge symmetry G superscript, and this B will be valued in a cohomology of degree n+1. Sorry, is there a question?
Sorry, did you introduce, I mean, maybe I missed this definition of the gauge field, because now we have this general framework. How do you define the gauge field in general?
So the gauge field is a discrete valued, it's basically a G valued element in the a G valued element in the P plus like degree n+1 cohomology of the spacetime manifold. And yeah, that's basically generalizing the notion that there's a one form background field for the zero form symmetry. And when you gauge this Gn n-form discrete symmetry, you are essentially summing over all configurations of this background gauge field, and you are essentially summing over all values of B in this partition function. But during this summation, you realize that there is no canonical choice of the phase. In other words, you have the freedom to add another term of e to the I times spacetime integral of small b wedge capital B, where this small b by degree counting is of big D minus n minus 1 degree in cohomology. So this small b is the background field of the familiar quantum symmetry that's originally introduced by Vafa in 1989. And in his context, it's 2D, where you gauge a zero form symmetry and you get a dual zero form symmetry, like G versus rep G or so. And later formulated generalized arbitrary dimensionality in this generalized global symmetry paper. So in quantum gravity,
sorry, but in ordinary, let's say ordinary U1 gauge theory in 4 dimension, this B what? I mean, B is what kind of object is B?
So in U1 gauge theory, so it depends on, so if you want this U1 one-form symmetry, electric one-form symmetry, then I think the background gauge field is basically the electromagnetic field strength, which is star F mu nu. And for U1 magnetic, the gauge field, the background gauge field is F mu nu. But there, the story is a bit different in that it's continuous, and I think the formulation of gauging is more conventional.
I see. No, but say I'm willing to replace this sum over B to as an integral or something. So I didn't mean like one form, but I meant like a zero form U1 ordinary U1 gauge.
But
is like a theta angle. What do you mean?
Yeah, but in the in the electromagnetism, the U1 zero form is a gauge symmetry. So here we're only talking about gauging global symmetry. So the context is a bit different.
No, but you can imagine that there is a global symmetry, abelian global symmetry, and then you are gauging it like an ordinary you compute the partition function as a background U1 gauge field, and then you want to gauge it. So I'm just asking what is the B in that case, the small b in that case?
Yeah, so as far as I know, the story of quantum symmetry doesn't generalize to the continuous case. So there are some recent discussion about symmetry TFT of continuous symmetries, which I wasn't following very closely.
Basically, what I'm trying to get at is that you are defining some sort of a gauging here.
Yeah.
And the gauging that I'm most familiar with is the ordinary one, which is the four-dimensional U1 theory. And you gauge, you have some gauge field and you integrate over it. Perhaps you can on a 2-cycle you can add a integral theta f type term, and so on. So just in that context, it's not quite thinking more, about quantum symmetries and so on. What is this? Is that phase essentially accomplishing these fluxes through 2 cycles?
Let's see if I were to couple to a background gauge field. Let's see.
I mean, okay, just so that so that we are in some familiar territory a little bit.
Yeah, the best I can say is that as far as I know, the unification of these two types of understandings is not very, at least not very systematically written in the literature of generalized global symmetries. So yeah, maybe someone has some intuitive understanding, but yeah.
Thank you.
Thank you. Yeah, I'll keep that question in mind.
Small b is supposed to be a background for the dual symmetry, right?
Yeah, for the dual symmetry, yes.
Does that work even when, let's say, the dual symmetry is categorical, like let's say B is non-Abelian?
For non-Abelian field, so for G being non-Abelian, then the dual symmetry would not be invertible. So here, for simplicity, we are dealing with the case that G is invertible. Yeah,
does the story generalize, or is it like when you have continuous symmetries, it just doesn't generalize?
Yeah, so basically G non-invertible is G being non-Abelian is the case that's somewhat considered by Vafa in 1989. So for him, this non-Abelian G, gauging that would result in a non-invertible symmetry that's parameterized by the representation algebra of G. Yeah, so that's the primitive interesting case that we will cover in part 1. Yeah. So this is what happens in quantum field theory, where we have global symmetries, but also in quantum gravity, there are this no global symmetry conjecture that's stated in Bank and Dixon in 1988, and later Banks and Seiberg in 1910, followed by more recent researchers. So they say that, sorry for the typo, but discrete global symmetries so basically there should be no global symmetry in quantum theories of gravity. And if you are using some incomplete description of this gravity theory and you appear to find some discrete global symmetry, then they either have to be gauged or they need to be broken. And if you further say that this gauging would create a dual symmetry that I explained in the context of quantum field theory, then the dual symmetry must also be explicitly broken by some dynamical objects that's present in the quantum gravity theory. So,
sorry to take you back, but just to go back to Abhijit's question, this some discussing equation 2 in some familiar context. Let's say that G is a U1 symmetry. I know you said it doesn't generalize to continuous cases, but let's see where this goes. Let's say G is U1 and we are in 3 dimensions. So it's a U1 zero form symmetry, and I'm trying to do this do an analog of equation 2. Would it work
let me say something that maybe will be helpful. So the gauging of continuous zero form global symmetry is known to have a Lagrangian description, like you add a term that's this Lagrangian, the background gauge field A mu coupled to current J mu or so. But I think at least it is believed by everyone who work on generalized global symmetry that gauging discrete symmetry is a procedure that nobody knows how to express in Lagrangian. And that is very confusing in either we learning or trying to explain to others, but I think that's the common understanding.
But
So
if you have a Lagrange, easier, right?
sorry, it can be expressed in partition function, but not in Lagrangian. But because it's some discrete, it usually happens in some discrete sectors of the partition function, whereas the partition function, by exponentiating the Lagrangian, gets some continuous information. I think this difference is quite a major one.
But just to complete my sentence, I was going to say maybe the face is like the Chern-Simons term, but it doesn't work.
Sorry, the phase, the Chern-Simons term. What did you say afterward?
I was trying to ask if the Chern-Simons term could be like the phase, because the small b that appears there would be f, and that would be like some current for a. And does it work in 3 dimensions? Is it the current for a dual?
Yeah.
The Chern-Simons term could be the so for Chern-Simons term to be the phase, you want some 3D space-time or so. So you want A wedge F or so. But the term, so the Chern-Simons term has some quantization.
B is playing the role of a gauge field. Small b is playing the role of a gauge field for the quantum symmetry, or some sort of field strength.
The background gauge field of the well. Let's see.
Small b in the new picture is supposed to.
Yeah, I think the small b and the big B should be playing symmetric role in that there's a sense in which you gauge twice and you go back. So
Okay.
Highly on equal footing. Yeah. Okay, thank you.
Sorry, one more question about, this about the second point about not having global symmetries in quantum gravity. Is this a perturbative statement already, or requires some non-perturbative?
I think it's conjectured to hold non-perturbatively, and there are many non-trivial tests in people who work on swampland or there are some intricate ways.
I was asking whether perturbative analysis should also not see global symmetry, or only after you consider the non-perturbative stuff should the global symmetry go away?
I think if you're in the perturbative regime, then maybe there are tests of this. I'm not so familiar, but I vaguely remember that people might have tested some of this. But if you say that in a non-perturbative regime and you focus on some parts that you can perturbatively access, then a priori you might see some artifacts.
Okay.
The usual argument I've heard is in terms of this topology changing when you have integrations of the metric. Do you remember what that is?
Topology changing when you have integral of the metric.
Yes, I was asking, since you brought up topological operators, like you could wrap them some other way, and then you would see that the charge is not conserved or something. Do you remember?
I don't remember a particular paper.
Okay,
yeah, okay, thank you.
Yes.
Yeah, so then these gauging of discrete symmetries are used in building non-invertible symmetries in 4 dimensions. So the efforts basically happen in 21, and what I will mostly be explaining is the non-invertible symmetries in the 4D continuum, like in 4D n equals to 4 Superhill-Mills theory. So the one that's easier to explain is called the half-space gauging approach. So I didn't prepare more, but it basically says that it basically says that there is these different polarizations. There is these different spectrum of line operators in a 4D n equals to 4 Superhill-Mills theory. Let's say there's SU4 and there's SU4 mod Z4. And among these two, and this SU4 has a Z4 electric one-form symmetry. And what this paper is saying is that you can also perform an operation of gauging the Z4 one-form symmetry so that you go to a dual theory, which is an SU4 mod Z4 with no discrete theta angle. And this gauging is highly analogous to the Kramers-Wanier duality in Ising theory, which exchanges the genuine operators for non-genuine operators. So remember, in Ising, like when a non-genuine operator, that like the density of spin sigma crosses the duality line, it will become a non-genuine operator mu. So by genuine operator, I mean that it has to stay at the end of a topological operator of one dimension higher, which then attaches to the duality interface. And here is the same story. So gauging Z4 electric one-form symmetry brings you to the SU4 mod Z4 dual theory with a Z4 one-form magnetic symmetry. And it is this gauging interface, you can stack it with an S-duality interface so that you go back to the original theory. And therefore, by stacking these two interfaces, you are getting a zero-form topological operator in the same theory, that's SU4, that's labeled by the Lie group SU4. And it is precisely this gauging step that, analogous to the 4D, to the 2D case, will bring you non-invertibility of the fusion rule. Yes, so this is basically a version of constructing the non-invertible symmetry in 4D n equals 4 Superhill-Mills that's easy to explain. And
is it known if there's a relation between the group you're gauging and the non-invertible line?
Sorry, between what and non-invertible line?
Is there a natural relation between the group you're gauging and the non-invertible line? Like, can you tell?
So basically, the fusion of the non-invertible line with itself will produce all. Let's see. It will produce the sum of topological operators that's charged under the invertible one-form Z4 symmetry. So more algebraically, if this duality defect is obtained by gauging a G-valued one-form symmetry, then the fusion algebra you would get is the Tambara-Yamagami category of G. So fusion of the duality defect with itself will be the sum of all elements of this invertible G.
Does the reverse folder, we have a duality defect that has exactly this fusion relation? Would there be a duality between the theory and its gauge version? I suppose that's
you're asking about relation between the theory and the gauged version. So in some sense, so by generalizing the 2D Ising case, you can say that they are isomorphic, but the isomorphism is less obvious. It's implemented by this SL2Z duality, by this SL2Z duality. Yes.
Thanks.
Yeah. And there's a second construction called TKRT stacking / KOZ approach, which is somewhat similar to the above approach, but not identical. And I won't explain the second one in more detail. And there are many activities to try to understand the stringy origins of these generalized symmetries. So basically, I could only be very brief about what happens here. So basically, both the charged heavy so basically the string setup looks for a quantum field theory which is obtained by compactifying string theory on a non-compact internal manifold. So recall, if you put string theory on a compact, like on an internal manifold with finite volume and no boundary, then you get a gravitational theory. The gravitational coupling constant will be inversely proportional to the volume. So if you want to get a QFT with no gravity, then you want the volume to be sent to infinity. Therefore, you get some internal manifold with asymptotic boundary. And so by putting string theory on such internal manifold, you can realize some quantum field theory. And it's interesting to study, and it has been interesting for me in the past few years to study the stringy origin of both the charged heavy defects and the generalized symmetry operators, the topological symmetry operators obtained by stringy setup. So in 2020, the charged heavy defects was understood to come from branes wrapping relative homological cycles of the internal manifold. So these are non-trivial topological cycles on the internal manifold so like usually people use the internal manifold that's a conifold singularity. So for example, C2 mod gamma, C2 mod Zn. And this C2 mod Zn has a boundary that's a length space S3 mod Zn. There are non-trivial one cycles in S3 mod Zn, which sits at the boundary of some topologically non-trivial relative two cycles that starts from the asymptotic boundary and extends all the way to the interior. And you can take D branes wrapping on these relative homological cycles so that you can construct these charged non-dynamical defects in the QFT. And whereas you could also have string constructions of the topological symmetry operators. So these are constructed by taking branes and wrap them on cycles in the asymptotic boundary. So in some sense, some people might find the understanding of this topological symmetry operator more intuitive than holography. So for example, like if you do ADS, so like if you do 40 n equals 4 supreme mills, then the holographic dual will be ADS5 times S5. And basically what people said is that the topological operator in the ADS are obtained by branes wrapped on cycles of this internal S5 mod gamma in some particular setup. And the fact that these gammas are like back in the geometric engineering setup, this S5 mod gamma should be thought of as the asymptotic boundary, and they're infinitely far away from the origin of the geometric singularity, so that if you take brane wrapped on them, then the dynamics of the brane will decouple, and you will only get some topological symmetry operator in the string, some topological symmetry operator in the string space, in the QFT spacetime. So in this way, one can engineer both. One can understand the generalized symmetries in 60 SCFTs very straightforwardly by engineering both the charge operators and symmetry operators. But basically I put these in the motivations. The reason I put these in the motivations is because these all rely on the particular string space-time setup. So I'm always putting this 10D or 11D string theory spacetime on a certain non-compact manifold and using some geometry of the internal manifold to characterize the generalized global symmetries. But
how do you see algebra in this D-brane picture? Like,
sorry,
is it
how do I see what?
These non-invertible symmetry when you have these D-brane?
Yeah, that's a very interesting question. So in the case of invertible symmetry, the fusion algebra so basically the topological operator you get from wrapping branes will carry a charge that is valued in some homology of the boundary of the internal manifold. And fusion, like invertible fusion rule, basically amounts to addition of the charge in the homology group in the internal manifold. So basically for S3 mod Zn, the length space, the boundary will have a first homology of that's Zn valued. And you can have one cycle that's valued 1 in this S3 mod Zn and another cycle that's valued 2 that has value 2 in this S3 mod Zn. And a fusion of two wrapped branes will give rise to addition of these two cycles. So you get a Zn valued fusion rule in this. Is it clear?
Yeah.
Thank you. Yeah. So then all these makes people wonder that all the above studies use space-time perspective of string theory, but as you know, the investigation of string theory like starts from the worldsheet, or like the worldsheet perspectives is very important, so that you have a 2D theory, and whatever target manifold you get is the space-time. So the worldsheet perspective is also important because sometimes you get interpolating configurations between two different target manifolds in that some intermediate configurations might not admit target space description. So the motivation of this talk is basically to understand the space-time counterparts of generalized symmetries on the string worldsheet. So basically we say that there's a 2D theory and we don't specify it, but we assume that it's one that's controlled by a certain fusion algebra. And we want to see what happens in the space-time. What constraint does this worldsheet fusion algebra impose on the charge operators of impose on the vertex operators of the space-time? So we know that like in the space-time that has gravity, the counterparts of these global symmetries on the worldsheet should somehow be gauged, but little more is known. So like in the meantime, during our research, there's a paper by Cordova and Rizzi at the end of last year, which studies the non-invertible symmetries of Calabi-Yau conformal field theories came out. So they have overlapping interest in our direction in that they clearly are interested in studying some CFD that is a sigma model. So, but like before our work came out, there's no technically direct space-time statement yet, but only some indicative effort of what we are doing. So with all these preparations, let's come to part 1, which is scattering on non-Abelian orbifold space-time, where I will rephrase some old results in this new light. So all we need is like selection. So like all we are hoping for is to understand how the selection rules are controlled by symmetries. So in the group theory case that G is a finite abelian group, then the constraint is really straightforward in that each element, like we can have the charge element labeled by charge states labeled by elements G1 through Gn of the group G. Then at an allowed vertex, we require that the product of these elements equals to identity. And otherwise, this vertex as a scattering vertex would be forbidden. Here, and conventionally, an outstate with charge Gi is seen as an instate with charge the inverse of Gi. And then one might ask, what if the states are labeled by algebraic objects other than groups? So now we need to reveal the case of the non-Abelian orbifolds that are understood in the 1980s. So these are strings on a non-Abelian orbifold M mod G, where G is a discrete group acting on M, and we assume that the only fixed point that G has on M is the origin. Like otherwise there will be extra difficulty that we don't want to handle for now. So as this illustration, this gauging will give quantum symmetry under which the twisted sectors are charged. And I'm going to draw an abelian Z6 symmetry for the purpose of illustration. So here you can have string states, and by the string states, you can get, by the string states in this auxiliary covering space M, you can get different states in the gauged theory that's either twisted or untwisted. So the untwisted sector state, as I draw in blue, that's a closed string, also comes from a closed string in the covering space. Whereas a twisted sector state in the quotiented spacetime that I draw in red will come from an open string in the covering space, but it is a special open string that the starting point and the end point of this open string is identified by this finite group action. So in this sense, their behavior is different, and the twisted sector state is labeled by an element in the group G that tells you to what extent is this, or by which element is this twisted sector state twisted. So the condition for the existence for the for these the various twisted sector states are labeled by conjugacy classes of G. So the reason you use conjugacy class is basically you can do a it's basically you can act by the group element on M, which both acts on the starting point and the end point, but such an action should be an automorphism of the end sector. So you get this modulo conjugation relation. And the condition for the existence of a vertex is now generalized to the form that for each in-state, you write down the conjugacy class that it carries, and you take a product of these conjugacy classes, and you will, in general, get a collection of a bunch of states. And all you require is that this collection contains an identity. So this physically means that there is one allowed fusion channel that a subset of these vertices can turn into the remaining subset of these vertices. And like when you see
this conjugacy, this product at the level of conjugacy classes, can I just think of it as each conjugacy class standing is representing a set of elements that conjugate to G1 and so on, and that there should be identity in this product of these elements in each
that's
set.
exactly right. So basically,
Okay.
I think you want to say that from each conjugacy class, I'm asking if I can have a clever way to pick out one representative so that their product identity. I think that should be equivalent to what's written here. Yeah, thank you. And in fact, that'll be used a few slides later. Okay, so right, yeah, I press and that's what you want. Yeah. So let me I repeat, equivalently, the condition says that I can find each element GI tilde that's inside the conjugacy class, sorry for the typo, the conjugacy class of GI, so that the products of all GI tilde equals to identity. Note that this condition clearly recovers the case that G is an abelian group in that there all the conjugacy classes would be of size 1, so their product has to be identity for abelian G. Okay, so let's look at scatterings at first tree level and then loop level. So at tree level, you generally get a tree diagram with n vertices and n minus 1 internal legs. So basically, you can show it inductively. And basically,
How you won't care about what exactly the orbifold is, whether it's C4 mod particular group, you won't care about that. Would you just work abstractly in terms of these group elements, or would you also pick a particular orbifold?
I will try to be as general as I can in the beginning, but here I do require that the action only have isolated fixed point as opposed to extended fixed points.
And what is the codimension of the fixed points that you require?
So isolated means that it's a point, and so the code.
Yes. No, that I understand. I'm asking you now a different question. Do you require a particular codimension also for the fixed point in 10-dimensional space?
So if you wish, I can, what I draw here, let's see. It can either be the full 10-dimension. Yeah, let me say that I don't require it for now. I can stay general.
I see. Because the nature of the orbifold is different depending on what kind of orbifold it is, right? For example, C2 mod ADE, gives rise to an orbifold which is fine, but C mod Zn has some problems, right?
Yeah, there's tachyons and there's.
Yeah. So I was trying to get to that. I mean, are you requiring a particular type of orbifold so that all these issues are not there?
Let's see. We're not getting realistic as there. So maybe you could think of it as we are like assuming that there are some configuration that have this fusion category have this orbifold and no tachyon. So you can think
Okay.
of yeah. Okay. Okay, so let's then see what happens for a tree diagram with a general number of vertices and no loops. So here, it's kind of tautology, or for now, you could think of it as tautology that for an internal leg, you can cut it open, and let's say the left side of the internal leg is labeled by a certain conjugacy class GA, and the right side of it is labeled by the inverse conjugacy class. And in this sense, if you want to write down the allowed condition for each vertex in the tree diagram, and then you multiply them, then the part of the internal leg can be trivially dropped because the product of H1 conjugacy class with H1 inverse conjugacy class will contain identity for sure. So in this case, it seems that you don't need to be too worried about the internal legs. Of course, I'm just drawing one internal leg, but it turns out that it's more helpful to think of it in terms of the representative element approach, because there you can see that there are some non-trivial counting that's working for the tree level case. So in terms of elements, let's say that we assign these conjugacy classes, and we are, for each vertex, we randomly pick a set of representatives of the conjugacy class so that their product is identity. And I have a set of G and I have a set of H. And as you can imagine, the element of the representative of GA and that of GA and that of H1 doesn't have to be the same. And if we want them to be the same, we can use some degrees of freedom to simultaneously conjugate. But what we can only do is that we can take a certain vertex and conjugate all legs attached to this vertex. So if we have two vertex, then the overall conjugation wouldn't make any difference of what we care about. So like the overall conjugation wouldn't be able to align the elements in a single internal leg. So we only have one relative conjugation that we can perform. And we can exactly use this single conjugation, let's say for all legs attached to the left point, so that we conjugate KGA K inverse to precisely match with H1 inverse. And for tree diagram, we exactly have n plus 1 vertices with n internal legs, but we also exactly have and conjugations that we can perform so that we remove all the internal misalignments of representatives, and we can just have them cancel. So in the end, for a tree diagram, the condition is that whether it is legitimate just depends on whether the conjugacy classes of all the external legs has products that equals to 1, so we don't have to care about the internal legs. But you will soon see that if you play this representative game for loop diagram, you will realize that you run out of internal legs. So basically, what you can do is that you can convert a loop diagram to a familiar problem, which is again the tree diagram. So for a loop diagram with L loop, you need to perform L cuts to turn it into a tree diagram. And where we choose to do the cut won't matter in the end. So if we perform these cuts, then we recover a tree diagram, and we know that we have enough conjugation so that all the internal leg representatives align. But this won't happen for the legs I draw in blue, which comes from internal legs before the cutting. So for L loop diagram, I will exactly have L pairs of external legs that I wouldn't be able to align, and they will weaken the condition. Because let's imagine that, so the question is, what is the set of G1 all the way up to Gn plus 1 that is allowed at, let's say, at one loop first? So, and the question, and basically to answer this question, I just need to figure out whether there is a choice of these sets of the labels of the internal legs so that each vertex is consistent. And if it is true that G1 through Gn plus 1 is allowed at tree diagram, I'm going to say that it is also allowed at any loop diagram, because I can just choose these blue internal legs to be labeled by the trivial conjugacy class. And the blue and the black lines that I've already chosen at tree level, that I know I will be able to choose at tree level, will work so that I know what to do for these blue legs. But even if the set of G1 through Gn plus 1 is forbidden at tree level, I still have the possibility of picking these blue internal lines cleverly so that each vertex is consistent for this loop diagram. This is because these blue legs will have H1 inverse, etc. So pairs of conjugacy classes that are conjugate to each other, and their product will in general contain not only the identity but also some other elements. So let's say at one loop, so I have one pair of blue leg, that's H and H inverse, and the internal contribution will give rise to the commutator. Let's say one leg has representative X and the other leg has representative K X inverse, K inverse. K is the conjugation. And their product will give rise to an element of G0. So the inverse here is just a convention. And so that the product of all the external legs no longer need to contain the identity. So here, what's allowed is that the product of the conjugacy classes of identity of external leg could either contain identity, which means it already worked at tree level, or also it could contain this G0, which comes from fusion of a pair of blue lines, which means that this set of external leg is not okay at tree level, but okay at one loop level.
Sorry, how what you're saying is the generalization of the fact that if you have, let's say, a bunch of pluses coming in and a bunch of minuses leaving, if it's a tree finite diagram, then the leg in the middle is this is going out, that doesn't work. Okay, let's say 1 plus 1 minus coming in, 1 plus 1 minus going out. If it's a tree diagram, the middle leg is neutral, but if it's a one loop diagram, you can have stuff running inside the loop as long as the net is zero. That's the statement, right?
Sorry, for plus or minus, do you mean that there's a Z2 group that's in effect?
I was thinking of U1, but yeah, let's say it's Z2.
Thinking of a, okay. I think here the net effect of the loop has to be, so you see the fact that G0 can be different from identity does require that X and K commutator is non-trivial, which requires that the group being non-abelian. So I'm afraid that this doesn't apply to
as
U1.
you said, consists of only one element. For abelian cases, the conjugacy class would consist of single element, and then the algebra would be that of a single element, right? As you said. So this, I think, requires this group to be non-abelian.
Right. Thank you very
But
much.
the main point is that when you have a tree diagram, the conjugacy class of the internal leg is fixed, and it needs to be one particular thing which you know from the external ones, and when you have a loop diagram, it's not fixed, and it's as not fixed as the internal legs.
In the non-abelian case, always in non-abelian.
Also in the abelian case, right?
No.
I mean, even in the abelian case, let's say you have U1, then if you have electron and positron going in, you have one leg, then the internal leg has to be neutral. If there's a loop, you can have random charge particles run to the loop, right? And the same thing.
No, but he is offering alternatives for the external states. For the external states, charges don't have to sum to zero in some sense.
Exactly. Yeah. So precisely because of the loops, we can have more flexibility on the set of external legs.
So how I was thinking, why is it, why do you want to work with the conjugacy classes? Why not just work with elements? Because there everything is clear. Every vertex, you should have a product to be one.
That's true, yes.
And then one can see the effect of that in the conjugacy class if one wants. But is it necessary to look at conjugacy classes?
In some sense, it is
labeling external states by elements.
But with elements, I do think that it's the description is not unique, but modulo conjugation of all legs attached to a vertex. So in that description, it's nice and clean, but you have some gauge degrees of freedom. So it's also nice to have an alternative description where you don't have gauge degrees of freedom.
Is this the kind of algebra that people encounter when they do correlation functions in symmetric product orbifolds?
Correlation function. I believe they care about more dynamics or so. I'm not super familiar with it.
Okay.
Yeah, so they're maybe part of what they care about is something has to do with G and something that has to do with the unorbifolded theory. Yeah, whereas we only care about what has to do with G.
Okay.
Also, with your multiplications, the multiplication of conjugacy classes is abelian, right?
That's true. Yes.
So suppose we look at group elements, you
so the conjugacy class algebra is abelian, but non-invertible. So there's elements. Yeah, so basically count the size of the conjugacy class too. Yeah. Okay. So so basically at higher loops, then at L loops, we will have L pairs of these blue external leg out of this cutting procedure. And this, after the repackaging this analogous to equation 7, we will get a product of L conjugacy of the products of L commutators inside this group, this non-abelian group G. So the requirement of the set of external leg G1 through Gn is that they only need to contain an element of G0 that's also contained in the product of these L pair of commutators as from the blue lines. So when we go to, so at finite loop, this the weaker constraint is actually less described, but at the infinite loop, we are essentially looking at the commutator subgroup of G. So it's probably not so commonly appreciated that the element of the commutator subgroup G commutator G is not solely consisted of commutators, but we only know that it is generated by commutators. And for some elements in G commutator G, it can only be written as products of generators of G, products of commutators of G. And so we know that at infinite, sorry, I don't mean at infinite group, but I mean at infinite loop order, you have a freedom that you only want this thing, that is okay if this thing takes value in the commutator subgroup of G, so that you need to mod out this part. And the remaining symmetry is G modded out by G commutator G, which is abelianization of G. So namely, the infinite loop charge group is the abelianization of G. And this is not very familiar from other perspectives in the context of strings on orbifolds. So we have explicit examples of string theory on product space, of like string theory on C2 mod gamma times some external space, where we ran this procedure and we can verify our general statement. And
Sorry, how do you verify? What do you mean by verify? Because I mean, I to understand what relevance is this statement that's infinite loop charge group. Why does one care about infinite loop? And how does one access that?
How does one care about infinite? Practically for simple orbifolds, you basically just need one loop. Like for C2 mod gamma, for example, you essentially just need one loop so that all the commutators they don't need to generate the commutator subgroup. They just span. They just at the set level give you the commutator subgroup. But in principle, if you want to look at the quotient by arbitrary group, then there are mathematically some groups. For example, there are two examples that's known in order 16, whose commutator subgroup has more elements than the honest commutators. Yeah, so we just want to accompany for this.
And you can verify this for C2 mod gamma and so on. This you mean at the algebra level, right? At the algebra level, you see these commutators, or is there a string theory calculation here?
Yes, yes, at the algebra level. Yeah.
I see.
Yes.
Okay.
Thank you. So as some comment on the literature side, there's one slide I skipped. So the fact that the non-Abelian orbifold gives, like, in non-Abelian orbifold, scattering at loop order get weakened, and like you get eventually weakened down to an abelian group, like already appeared at the level of Wards in a footnote in this paper by Hamidi and Wafa in 1987. And so it's also contained in a paper this year that's by Wafa and other collaborators that's coordinated with ours. So I mess up the number. It should be 2402 point, the same 5 digits. So it's submitted on the same day of ours. And they also had more explicit statements on string theory on ADS-CFT. So you're also welcome to check out their paper and talks, etc. So, right. And now let's go a bit general and beyond the old story of, in that this non-Abelian orbifold only gives you some very special fusion algebra. That's the conjugacy class algebra of this gauge group, of this non-Abelian group G. But what if we consider general fusion algebra C And in that case, can we still, so in that case, this C will constrain the tree diagram, but what happens to the loop diagram? And let me first skip the examples and move on to the general part.
Could you take it back?
Uh-huh.
So the statement is that if you have conjugate of a non-Abelian symmetry in string perturbation theory, it's weaker to an abelian symmetry at infinite loop level, right?
So it will be weakened to an abelian symmetry in the infinite loop scattering. Yes. Exactly.
So if I now can I now try to gauge this abelian symmetry, and then is it also true that any general non-abelian discrete symmetry in string perturbation theory is weaker to an abelian symmetry at infinite loop level? That sounds. So I was trying to think about gauging the final weakened abelian symmetry and get a dual abelian symmetry.
So the weaker symmetry in the space-time is already a gauge symmetry, I think. So somehow it's different than having a quantum field theory with this global symmetry and gauging it. So it's kind of tricky. It's kind of tricky to make sense of gauging this.
But what you have at the end is a global abelian symmetry.
Yeah, it's a global symmetry on the worldsheet, but it'll become a gauge symmetry in the space-time. If you let's say if you gauge this symmetry at the infinite loop level, then yeah, I think on the worldsheet it somewhat makes sense to think of this, and we haven't considered that. Yes. Thank you. So basically, the general question we want to pursue is that we want the fusion of local operators controlled, at least we want the fusion rules to be controlled by a general fusion algebra of C local. So we want to consider so for simplicity, we want to consider some simple case that is C modular. So in this case, the fusion coefficients Nijk comes from the modular S matrix and S0I, etc. And also in this case, so in the simplified case that C is a modular tensor category that we want to consider, the same fusion rule holds for both the local operators and the Verlander lines in the 2D theory. So Li Lj equals to Nijk Lk, and also Oi Oj equals to Nijk O super K. And the upgrade from fusion algebra to fusion category that will be interesting for future, but we won't handle today, is that at the level of the Verlander lines is given by different behaviors of the F symbols of the Verlander lines. And at the level of the local operators, I suspect it's given by resolving 4-point correlations into various 3-point correlations. And but we only consider the simplest case of focusing on what we can learn from the fusion algebra. And we also impose modularity. So scattering amplitude under a fusion algebra. So for a vertex, so for a fusion algebra, there is a fusion rule between two elements that also reproduces a formal sum of elements in this fusion algebra. And like the conjugacy class algebra is an example of this. So we say that a vertex is allowed still if the fusion product contains identity. So A1 dot A2 dot all the way up to AN contains the identity element. So we assume there's an identity element. And we also assume that there's a canonical Z2 automorphism that allows you to flip the direction of a state. So at loop diagram, we again perform the trick of cutting loops open to get tree diagrams. And the auxiliary tree diagram that we generate can be understood by combining the vertices inductively, and the interesting effect of going from tree to loop will be associated to the legs that we cut open, so we get a weaker constraint. But at an infinite loop, we will need to quotient a fusion category, a fusion algebra in some sense by a fusion subalgebra, and what will that produce? How do we describe it mathematically or understand it physically is quite challenging. But we will be able to show that the quotient is eventually a finite abelian group, and we will need to show it using the tool of hypergroup. So basically, hypergroup is something that we find from the mathematical literature that is a slight generalization of fusion algebra in that it's defined by having a set of elements xy, like xyz, etc., whose fusion rule looks almost identical to fusion algebra, but you no longer impose the fusion coefficients to be to be integers, but you only impose them to be non-negative real numbers. So nxyz or nxyz are all non-negative real numbers. So
sorry, can you flash the previous slide? I just want to see what the last line of motivation was. So you want to take the infinite loop case and try to see what sort of code abelianization it produces for a general. That's what you're after, right?
Exactly.
Okay, thank you.
Thank you. Right. So, yeah, so the hypergroup is basically a slight generalization of fusion algebra, and some important theorem that will be used will be phrased in it. So we are quotienting a hypergroup by a subhypergroup that's generated by all pairs of commutators. Sorry, by commutators, I actually mean that's generated by pairs of A1, A1 bar and A2, A2 bar, etc., where A1 bar is what you get by flipping the direction of arrow of A1, which we assume to exist. And for general fusion algebra, A1 plus A1 bar contains the identity, but it doesn't have to be, but it could be like the sum of identity with other elements in general. And also potentially with multiplicity.
A1 bar or A1 times A1 bar? What did you say?
Oh, I just said that A1 times A1 bar
okay.
Needs to be some multiplicity of identity, potentially plus some other things.
Yeah.
And basically the question is that we are quotienting some algebraic structure by some sub-algebraic structure. And the question is that the mathematical question is that such a quotient usually involves some normality condition, like whether we are quotienting by or like, does it even make sense to talk about a normal subhypergroup or so? And by delving into the math literature, it turns out that there are such notion of normal subhypergroup. And moreover, there's two different notions of normal subhypergroup. So there is a notion of normal if for H being a, let's see, for X being a normal subhypergroup of A, if H as a subhypergroup commutes with any element X in this hypergroup by multiplication, where this H times X is a bit more subtle than the familiar notion of multiplication of element with subgroup, like in the hypergroup case, is defined as the set of Y, so that there exists an element of H inside this subhypergroup big H, so that HX contains Y. So in more plain language, this subhypergroup HX means that you take all elements lower h and you multiply it with X, and you get a bunch of sums, let's say 3A plus 2B plus 1C, and you are taking this, and you are taking whatever shows up, whatever simple element shows up in the product, like A comma B comma C as a set to define what you mean by HX. And H is a normal subhypergroup if HX equals to XH, i.e. the multiplication doesn't depend on the order. So that in this case, the quotient of A modulo this normal subhypergroup H has a hypergroup structure. This is the baseline case. And there's a more special case in that H is supernormal, which is a stronger condition than normal, which is defined by the fact that the triple product of H for any element X inside this hypergroup A, the product of X times H times X bar, which is defined similarly as this HX, is contained in this hypergroup H. So in this case, it can be shown that whenever H is a supernormal subhypergroup of A, which just means this condition, then A mod H will give an ordinary group, which will be abelian whenever A is abelian. And these words looks very, very exhaustive, but if you follow the proof, it's actually quite straightforward to understand what they are doing. So essentially, they are some objects that's quite close to fusion algebra. So basically, let's also revisit some familiar examples. Let's say the Ising theory. So in this Ising theory, it's a modular theory. So the Verlander lines are given by like eta squared equals to 1 and n squared equals to 1 plus eta. So basically, what we want is that we want to quotient by products of charges of X and X bar. So X and X bar are signs of the pair of blue lines that's previously an internal leg, but we cut them so that they are a pair of auxiliary external leg. But they don't have to, but their product is usually 1 plus something. So this is the conj of A that we are essentially quotienting by, which is what having one loop is relaxing the constraint for us. So for the Ising case, we basically need to compute the fusion of anything with its orientation reversal with its conjugate. So we do this for eta and for n we get non-trivial fusion product. So at one loop, we are quotienting by this set of 1 and eta. And at L loop, what we are doing in practice is that for each concrete fusion algebra, we are not just focusing on products of one conjugate pair, but products of up to L conjugate pairs, so that we get this L loop of conjugate class algebra. This L pair of conjugate pair algebra. So for the Ising case, it's quite clear that it's sufficient to go to one loop, and we won't get more. And conj A of L will stabilize for L equals to 1. But for general fusion algebra, we could get conj A at 2 loop is larger than conj A at 1 loop. And we want the ascending chain of conj A subset conj A 2 loop and all the way up to conj A infinity loop. But we also know that the notation is a bit abstract, but we also know that for any finite fusion algebra to start with, this conjugate pair subalgebra will eventually stabilize to an infinite loop order for an infinite loop order subalgebra.
So it will be the other way. Conjugate not a superset.
Sorry, what's the question again? Sorry.
It's the conj is what you want to quotient by, I think.
I see. Okay. Thanks.
Yeah. So in practice, you repeat this exercise, and for more complicated fusion algebra, this conj A of infinity might contain more elements. But it's not been written down, but for us, it's a relatively straightforward application of using the definition of normal subhypergroup and supernormal subhypergroup to prove that this infinite order conjugate pair subalgebra conj A of infinity that we want to quotient by here is precisely a supernormal subgroup of A. And again, following the definition in the math literature is not more complicated than undergrad level algebra or so. Therefore, we know that quotienting A by this infinite loop subalgebra will give an abelian group, and a specialization of this statement is what we see in G and conj of G. But now we have shown that this would also be true if your fusion algebra does not necessarily come from the conjugacy class algebra of a certain finite group. So just as a term, we call this quotient a group this quotient of A by the conj A of infinite loop order as groupification of A. So in this book by mathematicians on tensor pedigrees, they give for a nice subset of case where A is modular tensor category, which is what we said above, they give a nice alternative way to compute the groupification of A. So they say that the groupification of A can just be computed by taking the invertible elements of A and taking the Pontryagin dual. So here the Pontryagin dual comes from the fact that by working with A, the scatterings, and looking at what are the weakening of the constraints of loops, we're working at the charged states. So it's the charged states. But then by looking at the invertible lines, the subcategory of invertible topological lines in 2D CFTs, we're looking at the symmetry operator side. And these two sides have the Pontryagin dual structure as we recall from slide 1. So if we want to show more concretely what I'm trying to say here, again, by the Ising theory, we want to say that if we want to look at allowed vertices, then at tree level, if we just want identity and this epsilon local operator to be on the external vertices, then we know that we must have an even number of epsilon vertices, where the convention is that like epsilon squared is identity and epsilon is absorbed by this operator sigma of dimension 1/16, 1/16, and sigma squared is E, is identity plus epsilon. But at loop level, now that it turns out that this constraint is no longer there because we can have a triangular shaped loop that's where this sigma element is running, and each vertex of epsilon sigma sigma is allowed because the fusion of sigma with itself contains epsilon. And following what we have done, you can also cut open this sigma leg so that you get a pair of sigma which fuses into E plus epsilon. This also tells you that your constraint is weakened. So
Sorry, how?
Mhm.
So is there any physical context where you would be drawing such diagrams in the Ising model?
Yeah, is this map connected question? Is this map connected to anion condensation and Kernelsman rule?
Let's see. Anion condensation in condensed matter.
But maybe you can first answer my question, which is more basic. Is this, would you draw these diagrams in any physical situation? Is there any physical question for which you would draw these diagrams? Just usually
Yeah, I couldn't think of one concrete question that, yeah, I
Okay,
hope.
so now maybe you can answer this more specialized question.
Yeah, so for anion condensation, I think in some sense anion are living in the 3D bulk of this 2D theory. So in some sense, these local operators all state as some particular anneal lines that attach that ends as this 2D theory as a boundary. And in this sense, there is a relation. And there is a quite precise description that maps these local operators with these anneals. And yeah.
But it's like the resulting symmetry structure, the same thing, like is it dividing by commutator GG if you're condensing?
I'm familiar with the anneal condensation terminology used by condensed matter theorists, but I am thinking on some follow-up direction of you not only using these untwisted sector states, 0, E, epsilon, and sigma, but also include all the twisted sector states. And then you see that the scattering can also be understood from the bulk perspective, where it's mathematically described by some tube algebra or so. But yeah, I hope to learn more about the condensed matter language of describing it, and also more in concrete physical setups that this can be useful. But we haven't.
So I was just trying to ask a broader question regarding that. So in the Ising model, we know this fusion algebra of operators. Is there any physical question for which this groupification is the answer?
Yeah, that's I hope I could be better at answering these questions. But let's see. So by the theme of this paper, we are having some longer term hope of looking at some scatterings in the standard model and see that for the vanishings in the standard, for some unexpected vanishings of standard model scattering at loop order, we hope to see that if any of them can be sort of explained by attaching charges of or elements in the fusion algebra, so that there are some nice fusion algebra that can match these vanishings or so. That's what
So does one expect that there is some sort of a non-invertible symmetry group at work in standard model?
There are some continuous ones that's constructed, for example, by Shuhan and friends, and also by Cordova and Omori.
Non-Abelian one?
I think Abeli, so basically some U1 value type of thing. Yeah. It's, for example, in his reveal, like in Maxwell theory, they have some continuous non-invertible symmetries, but like discrete non-invertible symmetry, people use less. Yeah.
Okay.
Thanks. Yeah. So I'm about to say that in this Ising theory, one can no longer use this local operator perspective to intuitively see that at one loop, you can allow 3 epsilon operators as external leg, which is not allowed at 0 loop at tree level. But you can also use this mathematical result by this tensor category book to do the shortcut, which is you look at all the local operators and you see that the invertible local operator is only this eta, so that the groupification of A is given by the group of the invertible subgroup of 1 eta, which is Z2. So you see that you get Z2 from both ways, but in some sense, this matching is quite non-trivial because in this in this shortcut side, in this invertible line side, this D2 is generated by eta, the order 2 invertible element. But on the other hand, in this local operator side, we are modding out this subgroup by 1 eta, so that we get in some sense, the equivalence class of identity and the equivalence class of the local operator sigma with non-invertible fusion rule. So there's some structure of punctual eigenduality involved in determining this Z2 in 2 different ways. And at some outlook of formally pushing or going into more non-trivial examples, one could in principle consider this Gepner model, which are orbifolds of tensor product of n equals to 2 minimal models on the string worldsheet. And so that this H has to satisfy some particular number theoretic conditions associated with the order of each minimal model so that you get a Gepner model. And for particular choices of these KIs, so basically these KIs will determine the central charge, which for sigma model cases will determine the dimension of the internal manifold and thus the dimension of the space-time manifold. So as was investigated in the 80s, for C equals to 9, there's like an internal 6D manifold, which gives you 4D space-time for type 2 string. And and there are some concrete examples. For example, a choice of 4 copy of K equals to 2 minimal standard SUSY standard model can be described by a space-time configuration of an orbifold of T4 mod Z4. And this description and this correspondence is not just one direction in T4 corresponds to one minimal standard model, but it's way more complicated than that, which I couldn't describe in a slide. And this correspondence is shown by these papers in 89 and also this paper in 99. So maybe it's somewhat, so like independent of the worldsheet interest, these quotients of torus as space-time configurations has been studied by some particle phenomenologists, like I remember Kobayashi and some friends. They identify that there are non-invertible. So yeah, actually this part is mentioned in the end of part 1. So basically there are these papers where they study a range of torus quotients as part of the space-time, like the simplest case of S1 mod Z2 that has an Ising symmetry on the worldsheet, but there are more complicated ones. And for example, for this T2 mod Z3, they're able to identify a non-Abelian discrete symmetry of order 54 that has this semi-direct product structure by examining the Z3 quotient on T2 carefully. And the connection for standard model is further elaborated by their paper also in 2006. So in fact, both this T2 mod Z3 case can already be viewed as the target of a Gepner model of 3 copy of K equals to 1. So we can have a worldsheet description of these phenomenologically interesting space-time torus quotients, which on the worldsheet have some larger fusion categorical symmetry of a few copies of SU2 WZW model. And it will be interesting to at least first reproduce what they have, what the space-time perspective has predicted about the non-Abelian gauge symmetry, and to see what new thing can we learn from the worldsheet fusion categorical symmetry. So this is a future direction to go. And I think I will basically skip this part 3. And yeah, thank you very much for listening.
Thank you very much.
Thanks. I could take more questions, or if you're interesting about what I'm missing, I could also talk a little bit.
So just one question about when you were giving the examples. I mean, one kind of category which is quite ubiquitous is this Worldsheet category or WZW fusion category, right? Where you fuse the representation of the integral representations of the Kac-Moody symmetry. So what is the groupification for that?
Right. We have that in an appendix where we worked out all the SU2 WZW model with ADE type of modular invariance and also the SU3. Let me check. Yeah.
Sorry, that's not the at the beginning, the conjugacy.
Uh-huh.
No, I'm asking, like, is the answer to Abhijit's question the conjugacy construction you showed us in the beginning?
Conjugacy. So
I'm asking what is the answer.
Yeah. So
yeah, I think
the division by the commutators of the right?
No commutators. You have this conjugate infinity.
conjugate pair.
It's not a discrete symmetry, it's some category, right? Fusion category.
Yeah, it's a G, right?
Hmm?
Okay.
So I think it's W. So it's the question is by taking this equation and for A being WZW, fusion algebra and ask what is the groupification. Yeah.
Because if I try to use equation 22, I don't find anything. Maybe I'm wrong, but I was just, or maybe I do. I don't know. I don't know how to think about equation 22 in that context. Because
So for SU2 WZW model, I think you have a bunch of topological lines that's so basically the elements are somehow labeled by spins, and you get right. Sorry, it somehow not loading. And okay, I'm opening the PDF. Sorry.
maybe ZK or something where K is the level. That
Yeah,
seems like the
exactly.
good option.
But it be you mean the final result?
Yeah, it depends on the level. Yes, and
Also should depend on n. So Zn times Zk, something like that. I don't know. What can it be?
so
There has
for
to be level rank duality maybe also.
exactly. So for SUN at level K, we say that all these groupification respects the level rank duality. So groupification of SUN sub K is the same as groupification of SUK.
So then is it just Zn times Zk?
I think it's not that straightforward. So let's see.
It has to be an abelian group, right?
ZNK.
Should be a abelian group. Yes.
Zn but they're prime Zn.
Yeah. So we say that for SU2 sub K, and for A-type modular invariant, the groupification is always D2, and the conjugacy class and the commutator length is always 1. And for SU3, so we say that for SUN sub K, the groupification is basically Zn, which is the center. So it's, in some sense, it's not super surprising. It's because the center will always will always be the symmetry in that. Right, there's a Zn center symmetry for each representation of this SUN. And yeah, when you fuse, you require that the center charge so it's an abelian symmetry and it persists at infinite loop order. And the level rank duality statement is somehow, let's see. What did I say? So it shouldn't be manifestly. So basically the level rank duality, maybe we deleted that because. So the mathematical statement I remember from the CFT book of level rank duality is that there are some difference between a Zn factor and a Zk factor when you exchange them. That's what I vaguely remember. Yeah.
That's why it's not symmetric.
Right. Thank you.
Okay, and one more. So here, I mean, this was kind of a general description of these, algebras, right? Various algebras and how it,
algebra.
but I mean, you phrase this discussion in the context of some sort of a string theory scattering, but it did not have been that, right? I mean, any quantum field theory where you have particles labeled by conjugacy classes of some non-Abelian group, you could do this and see what type of scattering elements will be non-zero and so on. So it doesn't have to be a stringy scattering. Is that correct?
Yeah, so this part of hyperalgebra is not yet have a stringy setting, but like for example, the future direction that I was imagining of saying that this Gepner model corresponds to that target space has like involves a stringy setting, and we hope to be able to say more there.
Okay.
Yes. Should be. I mean, you should say field theory answer.
Any questions? Okay, let's thank Hao again.
Okay. Thank you very much for your attention.
Thank you all.
Interesting questions.
Bye-bye.
Bye.